Hello, I'm going to go through the momentum equation lecture 7 from the module cive1460. Actually, we're going to go through lecture 7a, which is just half of the lecture, because we'll cover the second half in lecture 7b. Forces due to moving fluids. Well, we've all seen fluids causing a force. Well, aircraft fly because the resultant force on the wing is upwards. Jets of water hit targets, or jets of air, or you blow something, that's a force on the target. More practical engineering, water turning a turbine, creating electricity. If you hold the nozzle of a hose, you feel a force on that nozzle. What is that force? How are we going to analyse this? Well, with solids, you know about force equals mass times acceleration, Newton's second law. With fluids, we use the same Newton's second law, but we come up with an equation that we call the momentum equation, and it's a statement of Newton's second law, or F equals ma. But we won't use F equals ma, we will use something slightly different. Simple, but slightly different. Remember what F equals ma, it's the rate of change of momentum. So we're going to look at how we can calculate the rate of change of momentum. So we've got a fluid mass that's constantly moving. So what mass should we use? Well, we consider a stream tube. Right, here's a diagram of a stream tube. Remember what a stream tube is. It's rather like a pipe, and you can see here this is a pipe one that's getting wide, it's diverging, but the pipe walls are not walls in the stream tube. They're moving at the velocity of the fluid. Okay, so we've got here on the lower image a 2D slice through this stream tube. I'll switch my laser pointer on here. So here. Okay. We're going to assume steady flow, non-uniform flow. Steady, and that we've got a non-changing velocity, area and rho at the inlet and outlet, but that non-uniform because it's changing in area or velocity and possibly density as we go through. We can see in this picture it's a bigger density, bigger area, sorry. Okay. Now let's just have a look at this cylinder. Right, we know that we've got. Let me just switch to the pen here. We know we've got a fluid that moves a distance, velocity times delta t, inner time delta t. So it moves this distance here. That volume, if it's moved in through an area array, is area times that distance. So we've got a volume there. The mass is that volume times the density, so we multiply by the density. We call this rho 1. You know, all of these subscripts are 1 because that's the point at which the fluid is entering the stream tube. The momentum is the mass times the velocity, so we multiply all this by the same velocity, u1. So look at that, that's the momentum entering. Remember what Newton's second law is force equals rate of change of momentum. So we've got a momentum entering, and we can do very similar. See, we have a subscript u2 to get the momentum leaving. So we've got momentum leaving minus the momentum entering, all divided by the time at which this is occurring, delta t. So that equals the force. So that expression now on the screen now is the rate of change of momentum. We can simplify things. We can get rid of that delta t, cancel that delta t out everywhere. We know that Q equals A1 U1 equals A2 U2 from the continuity equation. And if we're having incompressible fluid, constant density rho 1 equals rho 2, and we'll just drop the subscript and put rho. Substituting those two into our equation, we get F equals rho Q U2 minus U1. This is the momentum equation. You might see in some text F equals m dot U2 minus U1. M dot is rate of change of mass, dm dt, and it's equivalent to rho Q. Rate of change of mass often used when we've got compressible fluids. We'll use this second expression here in all our calculations. You can look in the notes that come with this course for more details on the first expression. This force is the force on the fluid. It's in the direction of the fluid flow or the direction of the velocity, whichever you want to say. So these two velocities, U1 and U2, must be in the same direction for this equation to give us a single force. However, not all flows are in one single direction, so we'll look in a moment how we deal with 2- and 3-dimensional fluid flows. Here's the general 2-dimensional case. And what we do is resolve in the components, so x, y and z. We'll just look at x and y, x being horizontal, y being vertical in this diagram. And we just resolve the velocities in the x direction. Then we'll get the force that is in the x direction. So here is our momentum equation. Rho Q U2 cos theta 2 minus rho 1 cos theta 1. Or we'll write that as a subscript, second subscript x. So on the diagram here, we'll see U1x in the x direction resolved, U2x in the x direction resolved, and for the y direction similar, but it's sine theta in this case, and second subscript y. Force diagram, which you'll be familiar with, allows us to calculate the resultant force on this diagram. The resultant force is the green arrow, and we just get that from Pythagoras. F equals the resultant. F resultant equals square root of fx squared plus fy squared, and the angle of that resultant force is tan to the minus 1 fy over fx. So a summary of that, the total force on the fluid is equal to the rate of change of momentum through the control volume. Whatever is a control volume is any shape that you want to use that encompasses the inlet and the outlet. And the equation is rho Q U out minus U in, where those two velocities are in a specific direction. F is a vector acting in the direction of the fluid, on the fluid. So this force, we'll call this that we've calculated, let's just go back, this force F from the momentum equation is what we'll call now the total force. And we can say this is made up of three forces. The force Fr, which is the force on the fluid by any solid body, we might call that the reaction force, that's a subscript R. Fb is the body force which is essentially the weight of that force caused by gravity, and it will always act down. Fp is the pressure force caused by a difference in pressure between the outlet and the inlet. So the force at one end will be pressure there times the area there. So Fp at 1 is A1 times P1, and Fp at 2 will be F2 times, Fp2 will equal A2 times P2. So in summary, the total force is equal to Fr plus Fb plus Fp, and it's often Fr that we can't calculate, that we want to calculate, that we don't know. This Fr is the force on the fluid, and the reaction force R is the force on the solid. So it's the equal and opposite direction to the force from the fluid on the solid. Let's have a look at estimating the direction of the force Fr. You see we've got a bend here that's curving upwards, and the force that's going to act on the fluid is going to turn the fluid upwards. So I've drawn an arrow there because that's pushing the fluid upwards, pushing it in and upwards. So I'm sort of estimating where that force will be. It's always useful to estimate the expected answer before you do a calculation. That acts on the fluid there. Reaction force, and the green arrow there, is the force that's acting down on the bend. So that's the force that's trying to straighten out the bend, in a sense. As this force R is in the direction of force will act on the bend, we'll call it capital R. This is a force that can be very large in the case of water pipes. And in the case of water pipes, you've got to hold the pipe in place. It might cause breakage at the joints as the pipe moves. So here's a concrete block, which we might call a thrust block sometimes, and this is a heavyweight block that withstands any force on this bend to stop this bend moving. So if this is a force on this bend going that way, this heavy block will prevent it from moving. Okay, that concludes part 7 lecture, part of 7A of this lecture. Look out for another video for 7B.